Welcome to Brain Vision.
Okay, so for this problem, given the z component of the magnetic field, we want to determine the radial component of the magnetic field using the Gaussian law for magnetism. So here is already hinted by the problem that we can draw a Gaussian surface like this, which is a cylinder with length L and radius R. And the Gaussian law for magnetism simply states that the magnetic flux through any kind of Gaussian surface is always zero. So for this Gaussian surface, we need to consider three contributions. One is the flux through the top surface. The second part is the flux through the bottom surface. And third part is flux through the side surface. And their sum should equal to zero. So the flux through the top surface is given by beta L times the surface area of the top surface, which is pi r squared. Since the z component is uniform and there's no contribution from the radial component, and the flux through the bottom surface equals zero, because the z component at zero equals zero, and there's no contribution from the radial component. And finally, the flux through the side surface equals the radial component times the surface area of the side surface, which is 2 pi r L. And there's no contribution to this term from the z component. So we get this simple algebraic equation. And from this simple algebraic equation, we get the radial component equals negative beta r over 2. And next, we need to plot the top view and side view of the magnetic lines. So let's first plot the top view. So since the radial component points inward, we have magnetic lines that look like this. And for the side view, let's choose the slice of xz plane. So along the z-axis and along the x-axis, the magnetic field is zero. So we have these field lines that are very close to the z-axis and x-axis.